Hi everyone, my name is Krishnika and I'm a third year space engineering student. Thank you so much for coming for this event today. We really appreciate that. And I'm pretty sure at the end you all are going to get a lot of information about space engineering at York. So without much delay, I will pass it over to Professor Franz to take over the session.
Thanks, Krishnika. And you also didn't mention that you are, if I'm not incorrect, our student space engineering rep for the year. So
oh, yes.
an important role. And thank you for standing up and doing that. So
thank you.
I'm Franz, and I was the undergraduate program director for space engineering up until the summer, but I'm actually on sabbatical this year, so I'm not the UPD for this year. We're actually currently missing our undergraduate program director for space. So Jinjin Shan, who is the chair of the Earth and Space Science and Engineering Department, who is also a space engineering prof, is mostly standing in for that role where we need it for the year. So, but you can reach out to me at any point. I'll put my email in the chat at the end of the conversation tonight. Great to see a number of people, great to see some familiar faces. And we are recording the session for folks who can't join this evening if they want to watch it afterwards. But do ask questions, do feel free to unmute and ask real time, put questions in the chat, however you want to do that. So I will be talking about a subset of the things York does in space. So my engagement with space engineering in York has focused on primarily our CubeSat missions, and we have 4 that are either have happened, are currently happening, or may happen in future. So that's quite a lot for the university. And we'll be talking a little bit about the space engineering program. We'll be talking about the space missions that we've flown and are shortly going to fly. And we'll also talk about some possible future directions of the space engineering program that a couple of the folks in the room actually have been involved in a pilot of last summer. And we had a slightly strange version of it this summer as well, which I'll tell you a bit about later on. So let me see if I can get my slides to move on. So when we talk about space and space engineering, we will be spending a lot of time talking about CubeSats, but the paradox with space is it's really difficult to get there, and so very few countries really currently have means to get into space, although that is changing. But once we're there, you know, the boundaries between different countries' airspace don't obviously exist in space. So space is designed for the benefit of all of humanity. There are challenges to that with the space forces that are now being set up around the world. But what we look at in space engineering is really not primarily how we get there, what we do there, how we do it there, what the challenges of doing it there look like. But increasingly, I think we need to think about how space is an environment that also has a very strong geopolitical aspect to it in terms of how do we work in space, whose responsibility is it when we're in space, the fact that there are no sort of boundaries in that sense. So I'll be spending a chunk of the time tonight talking about these very small spacecraft. This is one of the big game changers in space in the last couple of decades. A CubeSat is basically a 10 by 10 by 10 centimeter spacecraft, or some multiple of that. And so these things, where traditional spacecraft might cost hundreds of millions of dollars for a geostationary satellite, or billions of dollars for something like the space shuttle or space station, to maybe tens of millions for something perhaps the size of a dishwasher. These CubeSats may only be a few $100,000. So we're starting to see space being used for things that we could never imagine using space for before. And so when we want to fly something in space, what we really need to do is come up with an application that requires a space sensor in the first place. So the reasons why we put things in space are that we can see a large chunk of the world, that we can observe from outside the atmosphere, that we can observe things that are beyond the Earth in terms of deep space, that we can work in a microgravity environment, which is hard to create on Earth. These are various reasons why we might want to put something in orbit. Once we know that we have something that we want to do, what we're going to do is do some space mission design. So within the space program, a key component to space engineering is to think about how we design missions and systems that can do stuff from space. And we do that design using simulation, using testing for the space environment down here on Earth or on aircraft. And then eventually we'll get to the point where we can build and fly them. And this is York's first spacecraft that was flown in the middle of the pandemic, the descent mission. We'll take a look at that a little bit later on. And that's the type of thing that we might go ahead and build and fly. So as we go through the build process for a spacecraft, we need to create the components, we need to design the mission, and then we need to put it together. And some of the ways that we might put a spacecraft together are shown here. In this bottom right-hand corner, we have a thing called a PLI-SAT. Anybody have any ideas as to why we might create a PLI-SAT? What a PLI-SAT might be? Feel free to type in the chat or unmute yourselves and suggest your answers. Why might we create something called a PLI-SAT? Anybody want to guess what it's made of? Which is where the name comes from. Yeah, the PLI-SAT is made of, not of PLI-SAT, it's made of, good guess, but no, it's made of plywood. So why do you think we might build a plywood version of our spacecraft? This is actually a microsatellite design that we built out of plywood. All of the boxes on here are different components of that microsatellite design. So we have a communication system, we have a battery, we have some electronics for the onboard computer, we have our magneto-torque rods, and we put all these on a piece of plywood that represents the spacecraft structure. And the purpose of this is to do a couple of things. One is to make sure all the boxes fit. One is to think about where our cables need to run and how long our cabling needs to be. So you'll see this is a mock-up of the actual cabling, so we can work out where to pin it down, how long to run it. And the other thing that the PLI-SAT allows us to do is work out where the center of mass of our spacecraft is. And for things like the magnetic controls for attitude control, we can actually control the pointing of the spacecraft in orbit around the Earth by using magnetic coils that will interact with the Earth's magnetic field. But we need to make sure that the boxes around those coils are not themselves generating an electromagnetic field. Things like transmitters might have electromagnetic field that they generate. And so by laying it out in a PLI-SAT, we can see where those fields might come from. Next thing we have is a thing called a flat sat. This isn't as flat as some flat sats are. What do you think a flat sat is used for? Some of you might have heard of the term flat sat. Anybody? We've got a quiet group tonight. So FlatSat is basically all the electronics components of your spacecraft laid out on a flat metal plate with some test harnessing connecting all the bits together that allow us to check electrical connections, power connections, communications between each of our systems as we're building up a spacecraft. So this is actually the FlatSat of the descent spacecraft that York built. And then in the top right-hand corner, we have a thing called TinSat. It's actually an aluminium box, not a tin box. And this is used to test out antenna patterns. So these are real flight antennas on an aluminium box. They put this in a huge anechoic chamber, one of those rooms that has absorbent material on the walls. That allows us to test the RF patterns of our different antennas. So this is actually that TinSat that we saw just a minute ago in a giant anechoic chamber. This thing itself is about the size of a dishwasher. The arm is probably about the length of a small bus. And the room is probably not far short of the height of the Bergeron building up in Kanata near Ottawa. It's the David Florida Labs that the Canadian Space Agency run. And so they have this giant anechoic chamber that allows us to test antennas that have a very large antenna pattern that we want to check out. Here is another example of a FlatSat. This is for a microsatellite, whereas previously you saw CubeSat. So we have a lot of different boxes here. We have a power generation system over the back, which allows us to simulate the power that the solar panels would get from the sun. And we have the computers that simulate what the ground systems would do. So the next picture is of environmental testing. So when we build a spacecraft, we want to test it to make sure it works in orbit. In the middle here, we have a large thermal vacuum chamber. So this door is the door to the thermal vacuum chamber. Behind it, you can just about see the chamber itself. The spacecraft is actually in the middle of this. This is actually, again, at David Florida Labs up in Kanata near Ottawa. But we've put the spacecraft in this strange cage. This is actually a set of halogen lamps on a metal frame that allow us to simulate the sun illuminating the solar panels. They also heat up the spacecraft the way that the sun would, purely from radiation. So we get a radiative heat on the spacecraft. We put this inside the thermal vacuum chamber, cool the chamber down to very near to absolute zero, and pump it down to vacuum, which allows us to simulate the cold of space, and we inject the heat of space with our lamps. And then we can simulate the vacuum environment of space as well. Great question from Michelle. What testing do we do at York? So we have our clean room, which I'll show you in a minute, which is where we can do our manufacturing. We have thermal vacuum chambers at York, typically much smaller than this. There is one big chamber that we're currently not using that has been used for large spacecraft testing. We do have the way to do thermal testing, where we heat the spacecraft up or cool it down. Well, I'll explain why we do thermal and vacuum at the same time in a minute, Taha, but that's a great question. We also have a table that allows us to do vibration testing. So this is actually, again, at David Florida Labs. This is a very large shaker. This metal plate moves up and down and will shake the spacecraft in one axis. We'll then rotate the spacecraft around, shake it again in a different axis. At York, we have a small version of this where we can test individual components and up to a small spacecraft. This thing over here is used to measure the center of mass. So it's a table that spins and it takes measurements of where the mass distribution at the spinning table is. That can tell us where the center of mass and what the moments of inertia of our spacecraft are. So in space, we're in a very cold and very hot environment at the same time. The spacecraft will see deep space on one side of it, which is at -273 Kelvin, and we'll see sunlight when it's not in the eclipse of the Earth on the other side, and that can get really quite hot. And then any heating sources inside the spacecraft can equally heat it up. So the hot side of the spacecraft could be at +100 Celsius, so 373 Kelvin. And the cold side could be at 0 Kelvin or -273 Celsius. So a fairly big temperature gradient over a relatively small spacecraft is quite possible. Okay. On the ground, the best type of test of the space environment is that thermal vacuum environment. But we might want to test vacuum to see if the material that we've built can survive getting into orbit, to check for manufacturing defects, to make sure there's no air pockets that are going to burst and break some electronics when we go into orbit. We might want to do some thermal testing to, again, check for manufacturing issues, making something hot and cold, we can get joints that might break. And so we might do tests on individual electronic units, unit level testing of thermal or vacuum. And then we might do a formal thermal vacuum test combined at the spacecraft level. Hopefully that addresses the question, Taha. So this is the York clean room, and this is when it was relatively empty. The other side of the room has some tables. This is actually, this is actually the descent spacecraft when it was being built. The clean room is currently full of the Essence mission, which is our second mission, which I'll be talking about a bit later on. And the reason why we build things in a clean room is the electronics and the solar panels and any switches and so on, if they get particles in them, obviously we can't clean those out. When this goes into orbit, we need to worry about material coming off, outgassing of materials that could potentially land on solar panels or optics that cause a problem. And so because once this is in orbit, we can't do anything with it, we can't fix it. We build it generally in a clean environment. We keep it in a clean environment until launch, and that hopefully reduces the risk of dust particles, metal particles, other things getting into the spacecraft and causing us a problem. So this next picture shows how spacecraft get integrated for launch. Down on the bottom right, we actually have some CubeSats. The thing that's blown up here is actually a slightly larger CubeSat. This is a 20 by 20 by 20 centimeter spacecraft. This was NTS, the Nanosatellite Tracking of Ships mission. This was an industry mission that flew a few years ago. On the left-hand side, we have a microsatellite. That's about the size of a dishwasher. And the large payload on top is an Indian Earth observation mission that would be the primary payload for the launch vehicle. We also have, you can see what looks like a solar panel mounted to the upper stage of the rocket. That's a payload that stays with the upper stage for the few weeks it's in orbit and allows us to see what's going on for a few weeks. It's a very low cost payload that would cost tens of thousands of dollars rather than hundreds of thousands for a CubeSat, tens of millions for a microsatellite, or hundreds of millions for the primary payload. All of this is the very top of a rocket. You can see the actual rocket tank itself just at the very bottom of the screen, and that then goes down a number of stories down to the bottom of the rocket. So this is as the payloads are integrated onto the rocket ready for launch. So what is space engineering all about? We do mission design, we develop the mission and test it. We then have to operate it. We equally have to do payload design and operations, and that includes various analyses of data. To do those things, ultimately, we're asking for money, spending it, hopefully providing value for that money. But a lot of space engineering is first of a kind or one of a kind type engineering. So in the field of engineering, space engineers often do sciencey engineering. They often do engineering that hasn't been done before. So that can make it quite an exciting field to work in. And ultimately, the hope is that space engineering is making the world a better place. And what we focus on in our current space engineering program is really the systems engineering you need to put together a space mission and the payload engineering that allows you to design instruments to interact with the Earth, with deep space, to detect what's going on from space. Those are the two areas of focus. So in terms of our curriculum, I'm just briefly going to go through this for those of you who are particularly wanting to know what we do in space engineering. We have 12 program outcomes that we're aiming for. So we're looking to have fundamental maths and physics skills needed to be able to look at space engineering, space science. We're looking at the systems engineering that I talked about in order to design space missions. We're looking to apply engineering design principles to sustainable engineering products. We're looking at the science of the Earth, the atmosphere, in order to be able to analyze these things from space. We're looking at simulation and robotics and control, which is needed for onboard systems. We're looking at signal analysis, electrical signal design, and communication, command, and telemetry systems, attitude control, and orbital control. The ability to actually create experiments to test and validate systems in payload design, system design, mechanical design, to build the structure, the tools that support this, like MATLAB, which you'll hopefully be familiar with, but also some orbital analysis tools such as SDK. And then an ability to actually explain the need for these missions to the public and to experts that can get us the money to build them, and explain to the public why they're needed, and manage the project of building space missions. So those are our 12 current program level outcomes, and they fit into our curriculum like this. So we have the 12 outcomes across the top. We have our 4 years down the page. You'll see if you look at the courses, I'm not going to go through all of them, but you'll see that we have a mix of maths, physics, mechanical engineering, electrical engineering, and computer science courses in our program, as well as the Earth and Space Science and Engineering courses. So knowing that space engineering is truly multidisciplinary, we work with our colleagues across the SON to bring in expertise, and with our colleagues in physics to bring in that scientific knowledge, as it's that sciencey type of engineering program. And the engineering courses that come from Earth and Space Science and Engineering are really focused in on those space applications. So space systems engineering, space mission design, physics and space environment, payload design, those type of core courses in with a space focus. Okay, so what has York been doing with this knowledge? We actually flew our first CubeSat, the descent mission, as I say, in the middle of the pandemic. So it was launched in, apologies, it's auto advancing. This mission was launched in the fall of 2020, so right in the middle of the pandemic. Graduate students did the design build work. It's going to keep on advancing. I'm going to have to keep pressing back page. And undergraduate students did support some of the work on it, but it was primarily driven by grad students, this first mission. And the purpose of this mission was to demonstrate a way to deorbit spacecraft at the end of life. Particularly with these small spacecraft, we have an issue that we're creating debris in space for future missions. So the goal was to launch 2 spacecraft that had joined together. And when they were tested out, we would deploy a thing called an electrodynamic tether. It's basically a piece of tape, metal tape, like aluminium foil, between the 2 spacecraft. This aluminium foil would collect charge from the background plasma field that's around the Earth. That charge would then be drawn down the spacecraft to the lower one, ejected back into the plasma. That creates a current. That current creates an electromotive force, just like any electromagnet, and that would then drag both spacecraft back into the atmosphere and burn up on re-entry. So that was the goal of the descent mission, to prove a re-entry device that could be used at end of life to allow spacecraft to be deorbited safely. So this is what went into one of the spacecraft. This was the upper of the 2. We had an onboard computer on our upper spacecraft consisting of a Raspberry Pi, so a very low-cost onboard computer. We had a Raspberry Pi camera that we could use to collect images of the Earth. And we separated our 2 spacecraft when we were ready with a simple spring. So we tied the 2 spacecraft together. We wrapped the tie around a resistor. We passed a very high current through the resistor that burnt the tie, and then the spring just pushed the 2 spacecraft apart. We also had a payload from Australia measuring background radiation, and a payload from Regina Lee's team looking at a different way to coat solar panels to get better performance out of them. Our lower spacecraft was the one that did all the communication with the ground. So it had the antennas to talk to the ground on it. It had a flight-tested onboard computer. It had the large transceiver from a spacecraft provider that was designed to do the space-to-ground communication. We used XB to communicate between our 2 spacecraft. It had the power off inhibitors to keep the spacecraft switched off initially. It also had this thing called a spin array. This is how, when the electrons that were being collected on our tether needed to be injected back into the plasma around the spacecraft, they get ejected through this thing called a spin array. A bunch of needles pointing out into space. The electrons fly down the tether and shoot out the end of the needles back into space. This is what the spacecraft looked like. This is this electrodynamic tether. It's basically just an aluminium foil folded up inside a big box. The box sits inside the spacecraft. These were some of the printed circuit boards. This is actually the onboard computer with 2 Raspberry Pis built into it, with that CubeSat shaped PCB design. This is the Australian gamma ray detector that we flew. This is the science payload from Regina Lee's lab, which had this moth eye anti-reflection coating on the solar panels. The goal is that any light falling on the solar panel actually bounces off these cone-like shapes and gets routed down to the panel surface. So we actually capture, hopefully, something like 30% more light than we would if we just had a flat glass plate on top of the solar panel. This is our 2 spacecraft almost assembled. You can see that we've now put the tether between the 2 spacecraft. It's anchored in one. We have the tether box in the other. We have the spring. This red thing is actually a magnetorquer, so a magnetic coil, so a simple electrical coil that we can pass current through to produce a magnetic force. In one of our axes, we've got our solar panels on. You can see some of the electronics. Here's the fully assembled spacecraft. This is the bottom of the spacecraft where we have that spint array. We have our cabling for our antenna. Our antenna board is actually around the edge of the bottom of the spacecraft, connected to the 4 antenna elements that deploy in orbit. We have our switches that separate the 2 spacecraft on the edges here. So we actually tie the 2 spacecraft together, and there's a resistor sticking out here that we wrap the ties around. And in orbit, we pass a lot of current through those resistors. They heat up, burn the nylon thread that's tying the 2 spacecraft together, and that causes the 2 spacecraft to separate. This was a test that we did, talking about testing. We wanted to test the separation mechanism. I don't have the video of this, unfortunately, but this was on a parabolic flight. So we took the spacecraft onto an aircraft that flies a parabolic trajectory. So it flies up to a high altitude and then basically does a nosedive. And as it's doing the nosedive, we get about 30 to 40 seconds of weightlessness. And during that 30 to 40 seconds of weightlessness, we had somebody hold the spacecraft, deploy the resistor mechanism to heat up the resistor, cause the spacecraft to separate, and they sprung apart, and we proved that our separation mechanism worked on board this aircraft as it was doing a parabolic dive. This is the vibration table where we shook some of our key electronics. We didn't shake the whole spacecraft, but we shook some key electronics. And you'll see that we used a bracket to shake in different axes. So you can shake the table in X, Y, and Z axes just by mounting brackets to allow you to change the orientation. That is the assembled descent spacecraft. This is just a detour to our ground station. So you'll see in the background, we have the Lassonde building. This is actually on top of Bethune College. We have a couple of antennas on the roof of Bethune College mounted on metal poles with, this is a UHF, VHF antenna with a mount that can turn in azimuth elevation that allows us to point these Yagi antennas out to space. We also have a parabolic dish. On the roof of Petrie, we actually have a few other antennas as well that you get to use in some of the courses. And during lockdown, we were running one of our final year courses using those antennas on Petrie roof. But the hope is that we'll be back to going to Algonquin Park, where there's a very large antenna that was previously used to test out blocking signals for GPS satellites, and you'll get to do some observations there as one of the final courses you do in your program. This is not a clean room. So because we launched our spacecraft during lockdown, we had to do some final charging of the spacecraft. This is actually Professor George Zhu's living room and kitchen. And so before launch, he had to take it and charge it and then ship it off to the States for launch. And this was done in a non-clean room environment because that's all we had. This is friends and family of the grad students who were working on the mission. This was in the middle of the night. This work can be long. And so the team that did all the hard work had their friends and family come to support when they did the final assembly. You can see the antennas haven't yet been tied down, but this was when they screwed the last screw of the spacecraft in as they finished the assembly. So this is the launch of the mission. It went up on an Antares launch from
the SS Kalpana Chawla takes flight, site set on the International Space Station.
So it was flown up to the space station, and then they put it on the outside of the space station in this pod structure. This had multiple CubeSats in it. And this is at the end of the Canadarm with the Dexter hand there. This allows them to manipulate this set of CubeSat pods outside the space station and then they kick all the CubeSats off space station in a sort of 45-degree down angle from the station so that they end up in lower orbit. You'll see the door opens, and we have 3 CubeSats coming out. Ours is the first one. It's the first 2 cubes at the front. Then we have a 1U CubeSat in the middle, and then we have a 3U CubeSat at the back. So we were one of 3 spacecraft kicked off at the same time from space station. You'll see the spacecraft starting to separate. And then this was our very first pass. This was the signal that we collected. Actually, we had a problem with the ground station at York. So this was the signal I picked up on my son's climbing frame in the back garden here in Cambridge. We were transmitting from York University. And we were picking up the signal in Cambridge. And this was actually a large data transmission that we achieved. We have a very strong signal from the spacecraft that told us we had a successful space mission.
Right, let's just enjoy this.
So
The strongest the signal is mainly in 29 degrees, but it's good enough for them. Wow, look at that.
and that was me getting rather excited about our space mission. But anyway, that's what we did with our first mission. We had great success picking it up. We did have some challenges achieving the mission goals, but the fact that we actually picked up a signal was huge. So what I'm showing now is ultimately that mission was to do with removing space debris. So I just wanted to show you some examples of some space debris. This is actually a telescope looking out at the geostationary arc. And these traces along here are actually stars, and the dots are spacecraft in the geostationary belt. Okay, so we have 2 spacecraft here. These are actually Telecom 2A and 2B. They're out in geostationary orbit, 36,000 kilometers above the Earth. We have some stars going past in the background. This was observed from a telescope in Provence in south of France. And we have this thing. This is actually a dead spacecraft in a slightly inclined orbit that was floating fairly close to our geostationary belt that could be a hazard to our geostationary satellites. So that's the type of thing that if we had a better means to deorbit, we could potentially deal with. Here's another one. You can see a very faint trace of a spacecraft in a slightly inclined orbit here. And here we have an almost polar orbiting spacecraft. And just to show you, this is actually the Astra constellation of spacecraft. So Astra satellites have a bunch of spacecraft that they operate. And those spacecraft do north, south, and east, west station keeping in a sort of slightly strange figure of 8. And that is that set of spacecraft dancing around. Just to give you an idea of what spacecraft at geostationary orbit look like when seen from the ground. And in, again, Regina Lee's group, she actually has a research group looking at observation of spacecraft from other spacecraft and from the ground to determine their attitude, their orbit, and to detect things like anomalies and space debris as well. So I'll watch that one more time. So that's our descent mission. That's some of the research work that goes on in the program. So on to ESSENCE. ESSENCE is York's second CubeSat mission that will fly. It's actually, we do have a 3rd CubeSat mission that has been driven by students that isn't yet at this level of development. The ESSENCE mission should hopefully go up in 2023. And there are people on the team in the room. And so the ESSENCE mission is built by undergraduate students, whereas descent was primarily built by grad students. And the purpose of the ESSENCE mission is primarily to train students in CubeSat design, and also to bring some of that training to the broader community, to schools as well. It's to launch a CubeSat to demonstrate various attitude control theories. This is a mission that's working with York University, Ryerson, and University of Toronto. And also it has a camera from Canadensis that will look at northern-ish Canada based on the orbit it's in, to look at the ice and the permafrost. So this is the state of the spacecraft model back at Delta PDR. The spacecraft is actually beyond this now. It's well into assembly. There's a couple of small issues that are being worked. But the hope is for the spacecraft largely to be assembled this month. Is that about right, Krishnika? And there might be some final tweaking needed after that, and then get it ready for shipping for launch in 2023. So again, we can see the flatsat. This is actually the descent flatsat, which we saw earlier on, but it's similar to the Essence flatsat with testing of subsystems. So first of all, we test the battery with the power system. Then we add the onboard computer to make sure that we can communicate with the two. Then we do some software testing on the onboard computer to different subsystems and different sensors. And then we actually add in the camera payload and other payloads. There's a modification of the sugar payload from Australia on this mission as well. And so all the payloads get tested together. So those are York's two, well, the one space mission that was launched and flew, the next mission that should go up next year. There is a proposal going in for a third mission soon. And then there is also the LastSat team, who are student designed CubeSat team, who are slowly moving towards a mission as well, but their timeline is slightly longer. So we have our current space program, which focuses on space systems engineering and payload engineering. But we've had the opportunity of the last 2 summers to do a trial of a new way to imagine an engineering education. And Michelle and Krishnika were a part of that first group who took part in this experiment, 6-week trial program last summer. This summer, we ran an abridged 4-week half-day program with 45 students from Egypt to try out a different way of running a program. But we have a green light to go ahead and prepare a proposal to make a change to the program. That doesn't mean it's going to happen, but it's good to know the types of things that we're imagining an engineering education could look like in the department. And we're trying out pieces of this in different places. We've had for the last few years our 2nd year space systems engineering course and our 4th year space mission design course collaborate. So the 2nd and 4th years get to work together. Your very first space course and your typically very last space course, you get the chance to work together to design a space mission. But what we're proposing, it won't be in time for most of you, but you might see the tail end of it if we are successful, is to have a space engineering program where over the 4 years of the program, you will actually design, build, test, and operate a CubeSat. So we will fly a mission every 4 years going forward. That's the hope. And the studies that you do will be integrated into that space mission. We will design it using space engineering practices of the future. So thinking about additive manufacturing, thinking about sustainable space engineering. And the goal is that all students work across all 4 years in a large space engineering team. So in that large space engineering team, Our fourth year students are the project managers, the systems engineering leads, the third years are the subsystem leads. The second years would then be the students doing a lot of the core work, in the first year students are doing some of the more fundamental work, and doing some outreach work as well as they get their feet wet. And so over the 4 years of a program, in our first year, we would have of the mission, we would have a mission concept review, mission requirements review, leading up to a preliminary design review of our mission. In our second year, we would get to our critical design review, when we freeze the design of the space mission. In the third year, we would assemble and test the space mission, going through test readiness, formal test review, and getting ready for shipment and operations. So getting ready for operational readiness review and launch. End of the third year, the fourth year of the program, we would launch, commission the spacecraft, operate it, and take some lessons learned. So if you joined at the beginning of this new structure, you would see exactly that flow. If you joined in the third year of the mission, your first year, you would be doing assemble and test. In your second year, you'd be launching and operating. In the third year, you would actually be doing preliminary design on the next mission. And in your graduating year, you would be the program lead doing the critical design of that next mission. So you get to see every phase of a space mission in this new program. A couple of things that we're wanting to include in this, again, if we get approval, is the idea that the missions would be for and with a community. So we're actually aiming to serve a community with the space mission, and would be thinking about sustainability from the ground up. How do we ensure that space missions are not adding space debris? How do we ensure that space missions are using materials that are not harmful to the atmosphere on re-entry, not harmful to the world as they're built? So the initial mission concept that the team that Michelle and Krishnika were on was looking at how could we help using space communities in Canada's north, knowing that we have a lot of issues around water quality. There have been water boil advisories in Canada's north for many, many years, and water quantity, that the amount of snow is getting fairly low in certain communities. So could we build a space mission with the community, for the community, that could help them have more of a voice around the problems with water quality? And the team also worked with a group of health students in Brazil who found very similar issues with indigenous communities in Brazil around water quality for the Amazon. This last summer, the Egyptian students then looked at the Nile being at the end of the Nile, and they went upstream to the source and said, in Uganda, Lake Victoria and the source of the Nile, they have again a similar problem around water quality and communities affected by that. So could we fly a space mission that could maybe help those communities, be built with and for those communities to actually achieve something of value? So this mission last summer got to a mission concept review, and the team did a wonderful job, and the website is still available. It's got some really good information on it. This summer, the Egyptian team got to a mission requirements review, and we may well take this mission up as mission 1 if we get approval for the full program. So that's one of the ideas that we're carrying forward. So in terms of this new program, what we're thinking is we would focus on 3 ways of doing assessment. So micro-credentials, working out how to use a tool like MATLAB. MathWorks actually provides some really good tutorials online, some certificates for some of the orbital analysis tools, the same. So let's not reinvent the wheel. Let's get you to go and learn those micro-credentials. Industry recognizes them, they're beneficial. If you get your amateur radio license, that's a micro-credential, and so on. As you design and build the spacecraft, you will get just-in-time instruction from subject matter experts, whether it's a colleague in mechanical engineering for thermal design of the spacecraft, or a colleague from our department on attitude control. As you design the mission, you will be given just-in-time lecture content and support related to the design of the mission that you're building. And then as you go through the formal gate reviews of the project, we'll bring in folks from industry and from the community to review the work that we're doing as a team to make sure that we're on track. And those will form the assessment in this new program, subject to finalizing and approval. We would connect in industry through hosting industry payloads, potentially through having the testing happen in an industry setting, although we do have facilities at York, being able to test some of the systems in industry would give exposure to what the test facilities and expectations are in industry. Have industry folks involved in the formal reviews, and then maybe at the end of the community use of the mission, there's a potential for entrepreneurship opportunity for a graduating cohort, or hand off to industry for some key pieces. So we would have the students from all 4 years working together on a number of different areas of the mission, covering technical and the non-technical aspects. So the licensing, the regulation of the mission, the connection to the community and making sure community is engaged and providing input on the mission and ready to support the mission when it's up and flying. The project management and the budget management, but also all the technical aspects of the mission. And some of the examples of micro-credentials are provided as well. Some of these you do get in the current program. If I can just step back. You do get the opportunity to get your basic and advanced amateur radio licenses in our current program. You do get exposed to a number of the tools like SDK, MATLAB, Orbit Determination Toolkit. You will go through WMIS training. You'll get some MATLAB and Simulink training. But there are some other things in here that would perhaps be more specialist for going through the space mission design. And there are a few other slides talking about different things that might happen at each phase of the mission, but basically that's all I wanted to talk about. So what I've hopefully given you is an idea of what the current program looks like and what people do with space engineering, a couple of our actual missions that we've flown and the technologies that we can use to track things in orbit that our researchers in the department do, and a possible future direction that we might go in with our program. On that note, I'm happy to open it up to questions. Just before we do that, if you are in your first year thinking, which program do you want to take? The one piece of advice I would give is it's worth thinking that the program you take is less of a decision that's going to close doors off and more one that opens doors up. So think about the different programs that we offer and look at which program do you think has courses that you might be excited about, that'll help you when you inevitably get to that point where things are a little bit busy and you're looking to get through the semester. If you're doing courses that you're enjoying, that are fun or that are engaging, it'll be easier to get through that. Having worked in industry for many years, in the space industry, I hired people with aerospace degrees. I hired people with mechanical, electrical, other degrees, and knowing colleagues in other industries, that was true for them as well. So an engineering undergraduate degree is really about learning how to learn engineering. So it's very much a pick your own adventure, find the adventure that is going to engage you, that you'll be passionate about, that you'll enjoy. And when you've got that degree, that doesn't mean you can't then shape your career in the direction that you want to go. That's my 5 cents on that topic. So over to questions, thoughts, comments. I've done far too much talking. Okay, how do you join a team that works on CubeSats like Essence? Wonderful question, Brock. If you're interested, Krishnika here will gladly take your name, and the team is always looking for extra bodies, especially at the minute, because there's lots of testing going on and getting ready for ops. So you just reach out and connect with the team, and they will let you know when they're meeting, and you'll get added to a what tool are you using? Slack or
Slack, yeah.
Slack channel, and that's all you need to do.
Sure, I will let Jack know about it. So Brock, you can join the team anytime you want.
That is really cool.
Wonderful.
Wow.
And it's an exciting time to join because testing is peaking right now, and then it'll be getting ready for operations. So that'll be the next challenge. We've got some issues that I'm failing to help the team with around communicating with the spacecraft from the ground segment. I haven't touched it for a little bit. I apologize to the team for that, but one of the challenges with juggling sabbatical. But the testing is advancing well on the space segment side, and the communication with the ground will get going soon, hopefully. Any other questions? Were there things that you saw that you were excited about? I took it from Brock's question that you were excited about the possibility of joining Essence, so that's good.
I'm looking forward to seeing the new curriculum.
Yeah, so this is one of the things I'm doing in my sabbatical is looking at creating the proposal for this new curriculum. And I will be very interested in student input on this new program, because one of the goals is to change some of the power dynamics in the classroom, where faculty aren't just there to give you knowledge. Faculty are there to be part of this program, as engaged and excited about the outcomes. So we're also looking at, we know that your timetables are fairly awful at the minute. So can we boil the structured piece down to, let's say, 4 days a week of 9 to 5, and then a day a week of flex working that you can do at some point over the other 3 days of the week. That's a goal that we have. So as we build this proposal, I will definitely be reaching out to anybody who's interested to get feedback. My goal is to have a first draft of a proposal for the end of the calendar year, so around the winter break. Yeah, to Michelle's point, the hope is that this will be a very different way of learning, thinking about having impact on the world as you do your studies. So the goal is that we could actually fly a mission that could help a community. We would engage with the community as we build it. We would empower them to be involved in the mission design. We would tell them what's feasible, but they would have the final say. We would hopefully be able to train them up to take over operations when we're finished our mission, and think about how to build it sustainably. There's a significant growth in the interest in space companies on sustainable design of space missions. And so the hope is that we can train the next generation of space engineering space engineers to be ready for that sustainable space work. And thanks for the input, Tahir. So the hope is that a program like this, obviously for people who are excited about space, gives you a feel for what it's like to actually build a space mission, but also with community and with sustainability built in. But to your point, Michelle, and to the broader picture, the hope is that people who go through this program could equally work in any other field, because they've then experienced an end-to-end project and all aspects of that project, the financial, the legal, the project management, the team, a complex big team, and the technical aspects. And so in terms of recruitment, we are wanting to think about what would the entry requirements for a program like this be? How do we ensure diversity of voices in a space like this? If we're designing it with a community, can we offer up spots to people in the community who are looking to go on a learning journey like this as part of it? Can we break down some of the barriers of cost by having scholarships pre-built into a program like this? We would need science voices and engineering voices in a space like this. So how can we make that happen? And then space engineering could be a test ground for this. If it works, why couldn't civil engineering build a sustainable building every 4 years? Why couldn't political science come up with a new policy every 4 years, or new form of governance every 4 years? So we're trying this out as a play space for imagining new ways of learning, we hope, but ones where industry buys into the idea and validates it, where students are keen and excited, and where faculty are ready to support it. So we've already reached out to various folks in industry who are really excited about it. We've done a survey of grade 12 students across Canada who've expressed interest in this type of approach. And this year we're putting together the proposal. So we'll see how it advances. Other questions? Great question, Brooke. So a lot of what comes from space missions is that space science or data, depending on the mission. So a lot of missions are government missions, and the data are often then freely available to the public, whether it's Earth observation, weather data, science data for deep space, or whether for other purposes. There are also a lot of commercial missions where that data is provided for a fee. So it depends on the mission. The places that you can find that public data, obviously well-known sites like the NASA websites, the Earth observation missions have a lot of data on specific sites. For example, EUMETSAT, the European Meteorological Satellite Organization, put all their satellite images out on the EUMETSAT website. Earth observation missions run by governments, you'll often find the government space agency has access to that data, whether it's CNES for the French missions, or CSA does provide some RadarSat data, although RadarSat does have a cost to it. Thanks, Michelle, for being here. Great to have you. Great to see you again. And we'll definitely be in touch as the proposal comes together this year. So looking forward to talking about that further. But yeah, so there is a lot of data available. And looking at the programs within our department, the geomatics folks are heavily involved in actually doing some of that data analysis, because they're talking about geospatial data. So spatial, temporal, spectral information. How do we geolocate it? How do we visualize it? How do we interact with it? And then the Earth and atmospheric science folks are often the users of the data, actually wanting to see that information from space, whether it's our planetary space science or our Earth science folks looking at atmosphere or Earth data. So that's how our department has historically fit together. time that data analysis. But the space mission design will often include getting the data down from the spacecraft, turning it from raw information into engineering values, technical values, and then getting it time-stamped and correlated so that it's ready for scientists to take it on and do something with it. Okay. Great question. And just for information, for our York University missions, we are trying to make some of the information available. If we get our feature program ready, the intention is that the communities would be able to share that information freely. And we're looking to make the designs open source as much as possible, open technology, so that, again, the community and society can be engaged in the design and the data that we collect. So that's the goal. Thanks, Brock. Much appreciated. Thanks, Tahir. If there are no other questions, then great to have seen you. Great to have had the chance to talk to you. And I guess we'll call it a day there. Does that make sense, Krishnika?
Yeah. Thank you
Perfect.
so much for attending, everyone.
Yeah, great to see you. I will stop the recording now.